Okay, so section 3.5 is going to kind of complete our work with polynomials, and we're going to do it by taking note of a couple things. Now, I used to print out something that I called the Root Finder's Toolbox. And it was this big handout here, has a lot of stuff in it, but I stopped doing that because a lot of these things I don't even teach anymore. And it's not that they're not cool or important, it's just that technology means we don't have to use these anymore, like the upper bound theorem or the lower bound theorem, or the somewhat challenging Descartes' rule of sign. They're all really cool things, but you know, the things that you need, right now, there's just two of them right here. Let's take a look at those two. There's one called the N Zeros Theorem. Basically what this says is that every polynomial of degree 4 has 4 values that would make it equal to 0. Now that's counting repeats, so if you have a root that's a root twice, you count it twice. Or it also counts complex values. So the bottom line is that there's a nice correspondence between the number of the degree and the number of solutions that a polynomial is going to have. There's also another one called the Imaginary Zeros Theorem that I'll come back to after a couple examples. But let's start by looking at example A, and let's do it on the handout here, right here. It says, true or false, the polynomial P has 3 real zeros. Now I included the graph of P, at least a little bit of it, right here. Let's take a look. How many places do you see this graph crossing the x-axis? And I'll assure you that it doesn't double back on itself and cross it someplace else. It keeps on going up to the right and down to the left. How many places does it cross the x-axis? 1. Now the important thing is that straight through, bounce, or wiggle? Which one is it?
Wiggle.
It does kind of look like a wiggle. But if we look in the graph, look at the graph a little bit closer. Let's go back up to example A here. Let me zoom in a little bit. If you look at that graph a little bit closer, let's take a better assessment of it. Bounce, straight through, or wiggle?
Straight through.
Straight through. So that means it has a multiplicity of what? 1. Right. All right. So perfect. It's got a multiplicity of 1, and we can kind of see that when we start looking for the roots of this polynomial. And come on, stop doing what you want and do what I want. Thank you. And so if you're trying to find where this actually equals 0, we can set it equal to 0 and solve. So P of x equals 0 means x cubed plus x equals 0. Now, if I was solving this for myself, I'd probably start by factoring this. So that would be x times x squared plus 1 equals 0. Okay. I want to know where this is equal to 0. Well, I can see the one that we already saw, right? We can see that when this times this equals 0, either x equals 0 or x squared plus 1 equals 0. Now let's see if we can't solve where x squared plus 1 equals 0. That's going to mean x squared equals negative 1. Take the square root on both sides. What did I forget there? Yeah, I need that plus or minus, right? So I need plus or minus square root of negative 1. What is the square root of negative 1? I. So I get plus or minus I. And if you look at that, I've got a total of 3 solutions, right? I've got a solution at x equals 0, x equal I, and x equal negative I. So x equals 0, x equal I, x equal negative I. And now I can write this polynomial as a factor of linear factors. So this is just going to be x, this is going to be x minus I, and that'll be x plus I. And all I'm doing to get the factors is trying to figure out, well, where do these terms equal 0? And then if I multiply those terms together, where they equal 0, here, here, and here, then I'll get my polynomial. So let's do that. That means that P of x can be written as x times x minus I times x plus I. Now the part that got covered up by my graph here says the polynomial P can be factored into linear factors with real coefficients. Are all these real numbers here? No, they're not. So this part would be false. This part is false too, because the polynomial didn't have real zeros. Not all three of them anyways. It had one real zero. That's okay. All right, so how are we looking on example A? Not bad there. We accounted for all the solutions. We had 3 solutions because it's degree 3. One of them was real and 2 of them were imaginary. All right. Let's move down to example B. Maybe a little bit easier to see over here. Polynomial is x to the 4th plus 9x squared. It says find all the zeros, real and complex, and then factor P completely. All right. Well, we can work on this much the same way we did the previous one. So I'm going to start out by setting this equal to 0. Then we're going to factor. How can we start the factorization here?
Factor out x squared.
Yeah, factor out the x squared, which leaves behind x squared plus 9. And I want to know again where that's equal to 0. So let's see what we can do. Well, this is a product of two things that equal 0. One of these has to be 0. So that one possibility here is x squared equals 0, which really means x equals 0. By the way, what's the multiplicity of my root here at 0? 2. So what kind of behavior should I see from the graph if I were to look at the graph at x equals 0? Bounce. Good. So let's take a look and see if we get a bounce there. So right at 0, oh, there's my bounce. And in fact, that's the only real root that I see. So if I have 2 real roots, what else do I have?
2 imaginary.
Yeah, 2 imaginary roots, 2 complex roots. Both of them are synonymous. So I expect 2 complex roots. I'm going to get them from right here. X squared plus 9 equals 0, which means x squared equals negative 9. X is going to be plus or minus the square root of negative 9, which is what? How does the square root of negative 9 simplify?
Plus or minus 3.
Plus or minus 3i. Thank you. Okay. Nice. Nice. So I've got all my roots. 0, 3i, and negative 3i. It's time to write P completely factored. Let's see if I can't do that. So I've got a root at x equals 0. In fact, the double root. X equals, I'll just leave it at 0. So x equals 0. And then x equals 3i. As a factor, that corresponds to x minus 3i equals 0. What's the corresponding factor to negative 3i? X plus 3i. And this is already equaling 0, so we're good there. P of x is then going to be the product of all 3 of these. So P of x is going to be x squared times x minus 3i times x plus 3i. Beautiful. Beautiful. So we found all the roots and we found all the factors. So the roots, those are right here. Roots, factors, and then the factored form of your polynomial. Nice. Nice. Sailing through example B, I hope. Thumbs up? Yes? All right, good deal. Let's keep going with example C. And we'll take a look at the graph there. So I'll shut that off. Look at example C here. And looks like I should probably zoom out a little bit. So let me do that. And that's not enough, so I'll zoom out some more. And, well, I think I've zoomed out a lot. I'm only seeing one real root. Where's our real root? 0. Yeah, all right. It's nice and easy to see that it's 0 there. So that's reflected in the fact that you can factor out an x, which leaves behind x squared minus 4x plus 20. Okay, not bad. Let's keep going. Now I want to solve where this is equal to 0. And generally speaking, I love to factor, but I can't see how this is going to factor. So if I'm trying to solve where this is equal to 0, I already know where that's equal to 0. I've got to figure out where this is equal to 0. How am I going to do that?
Quadratic formula.
Yes, thank you, David. Quadratic formula. Now, let me give you a little suggestion here with regard to the quadratic formula. Whenever you have a negative value for b, take the time to write the quadratic formula with parentheses, empty parentheses first. So like negative of parenthesis plus or minus the square root of negative parenthesis squared minus 4 times parenthesis divided by 2 times parentheses. So let's fill all that stuff in. I hope that you remember the quadratic formula. Let's see here. That's going to be negative of negative 4 plus or minus negative 4 squared minus 4 times a, which is 1, times c, which is 20, all over 2 times 1. The reason for my insistence on you putting those parentheses in first is because there's 2 places that people typically make a mistake, especially with a negative value for b. One of them is this negative, double negative stuff right here. All right, it's very easy to miss the double negative if you're not being careful. The other place is right here. When you square this, what should you get?
16.
16. But when people, positive 16. When people don't put parentheses here, a lot of times you get negative 16. So anyways, there's 2 places you can make a mistake very easily. 4 plus or minus the square root of 16 minus 80 over 2. And now comes the wishful thinking part on behalf of a lot of people. A lot of times people give me 64 here. Now 80 minus 16 is 64, but that's not exactly what we got. Should be negative 64. People just want to overlook that negative because that means there's extra work here, right? What's the square root of negative 64?
Plus or minus.
Yeah, so we're going to end up with 4 plus or minus 8i over 2. Now, you can and should factor out the 2. That's going to leave behind, when you cancel out the 2, 2 plus or minus 4i. All right, I'm kind of glossing past a step here a little bit. If you're curious about that step I'm skipping, let me kind of show that to you here. You can factor out the 2, and that leaves behind 2 plus 4i, 2 plus or minus 4i. And then those 2's cancel. So, now there's other ways you can do it. I just did it that way out of convenience. But here we go. Those are our 2 solutions combined with x equals 0 up here. Let's see if we can't write this as a product of polynomials, or binomials, or I should say, product of linear factors. So that's going to mean P of x, let's see, let's write our roots. X equals 0, x equals 2 plus 4i, and x equals 2 minus 4i. These numbers can move across the equal sign. I'll still have x equals 0 here. Here I'll have x minus 2 minus 4i equals 0, and x minus 2 plus 4i equals 0. Those are the binomials that I wanted. So this one, and this one. So that's going to give me my P of x. And just right here. So P of x equals x times x minus 2 minus 4i and x minus 2 plus 4i. Let's wrap that all up in one nice neat package right here. That's my solution. It comes from a product of all these linear factors that I found after I found our roots. Whew. All right, I think we got our money's worth out of side A out of our handout. Are we looking okay with that one? All right, all right. Sydney, doing okay there? All right. Let's move on to example D. And I guess the first thing I want to do is I want to go over a little reminder for us. So example D. And that is this. Sometimes you have the sum of cubes, and sometimes you have the difference of cubes to deal with, and or slash factor. So this is just a reminder. Sum of cubes would be something like this: a cubed plus b cubed. Difference of cubes would be kind of the same, a cubed and b cubed, except what's going to go in between here? A minus. Now in both cases, you're going to get a binomial times a trinomial. So 2 terms times 3 terms. The 2 terms part is just going to be what are you cubing to get each of these. So it's going to be an a and a b for both of these. For the 3 term part, what I recommend is you take a times a and get an a squared, and then b times b and get a b squared. And then because I know I need one more term, and I've already done a times itself and b times itself, what I'll do is I'll take a times b. And that gives me another term.
What is the 2ab for?
2ab is if you had a squared plus 2ab plus b squared would be a plus b quantity squared. So if you're thinking like, well, shouldn't there be a 2 there? If I square this out, I get a squared plus 2ab plus b squared. The difference here is I don't have that 2. So what that's saying is that you can't factor this any further. Neither of these factor any further. If that was a 2, then I'd be in great shape, but it's not.
Okay.
Now this is the same up here. A squared, ab, b squared. So, okay, great. Now, the only difference then comes down to the signs. Soap, exactly. SOAP stands for same sign, opposite sign, and always positive. So take a moment for yourself right now, or pause the video if you have to, and see if you can't fill in these signs using that idea that these two signs are the same, and then opposite, and then always positive. And that works for both formulas. Notice that they're both essentially the same. All right, we're going to take an extended pause here for just an extra second. Okay, sorry about the extended pause. Hopefully you finish this up correctly. Same sign, positive, opposite sign, negative, always positive. Same, opposite, always positive. So just kind of a little reminder there in advance of example D. Let's take a look at example D and see what's going on there. Okay, so they give you this polynomial and they also give you a hint. They say hint p of x and factor down like this. All right, that's not a bad hint. It kind of gets you going, but it doesn't completely solve everything for us. In fact, let's take a look at the graph here and see what we can figure out on our own for this. So I'll shut off C, turn on D, and well, I only see two roots. One of them at -1, one of them at 2. Inasmuch as this is a degree 6 polynomial and I see 2 real roots, what's that mean about the remaining 4 roots?
They're imaginary.
Yeah, they're all imaginary, they're all complex. So, that's going to be a lot of work for us. Remember that kind of recall work that I just did for you, where we factored the difference in sum of cubes? Can anyone suggest a reason for that?
So that we can use it for this.
Yeah, so we can use it for this, right? It's called just in time. I mean, manufacturers do that stuff every day. Just in time delivery. Well, this is just in time. So let's see if we can't figure out how these factor. Now I'm going to kind of put these in some colors here so you can kind of follow along. We'll do this one in pink. And then we'll do the other one in green. So here and here. Each of these is going to be a binomial times a trinomial. So what you should be asking yourself when you try and factor these things is, all right, well, what do I cube to get both of these? Well, I cube an x, and here I cube a 1. So that's the first binomial. Now from here, I made a suggestion. I suggested that you take this term and multiply it by itself. So x times x, that gives me my x squared. And I said, all right, we'll do 1 times 1. That'll give you another part of this. But I still need one other part of it. How am I going to get that middle piece here?
X1, which is x.
Yeah, x times 1, which is just x. Excellent. Robert, what signs go in between here, please?
Which one?
In all, right here.
Plus.
Plus, good.
Minus.
Minus,
Plus.
good. Same sign. Opposite sign, always positive. Excellent. Now, if you're watching this at home sometime in the future, then what you can do is pause the video and try and factor out x cubed minus 8 by yourself. And you want to approach it kind of the same way. Figure out, well, what do I cube to get this? What do I cube to get this? Those are going to be your first two terms, and then we're going to go on from there. Julian, maybe you can start us out. What's going to go in this first binomial?
X and 8.
Not quite an 8. What do you cube to get 8?
Oh, 2.
2, there you go. And then I'll take x times x, 2 times 2, and x times 2. This times itself, and this times this. That'll give me the middle terms, x squared plus 2x plus 4. And actually, I think I kind of gave away something, but that's all right. Same sign, opposite sign, always positive. Yay. Woo. All right. Don't worry, we're almost a quarter of the way there. All right. I just can't help but thinking of, in the Boston Marathon, there's a series of hills near like the 20-mile mark called Heartbreak Hill. And it's like a series of 4 hills. And the last one is just a real grinder because you're already 20 miles into this race. And when my dad ran it a bunch of years ago, somebody was on the 3rd hill with a heart, picture of a heart which was broken. Oh, this is Heartbreak Hill. And this is his first time running it. He thought, oh, great, I'm done with it. And then he realized that the person was wrong and he had another entire hill to get up. So, ouch, that's be kind of a bummer. But at least we know that there's still a lot of work left to do here. Because we've got, this is still example D. Example D. P of x is x plus 1 times x minus 2. And I'm messing with the order a little bit out of my convenience. I want to know where this whole messy thing is equal to 0, and I want to be able to factor it. So, wow. Now, if I set this equal to 0, I can see a couple places where this is 0, right? What's the low-hanging fruit? Where are the roots here that you can easily see where it's equal to 0? Yeah, -1 and 2. Thank you. But the other ones are going to be a pain. we have to figure out where does x squared minus x plus 1 equal 0, or where does x squared plus 2x plus 4 equal 0. And the solutions to these necessarily have to be complex, right? Because we already found the 2 real roots, and we know the other 4 have to be complex. We didn't see where it crossed the x-axis. So that means, more than likely, quadratic formula.
Nice.
Yeah.
So
And not only that, as a bonus, you get to do it twice in one problem. I know, it just doesn't get any better than that, right? So let's take a look here. Yeah. Don't worry, I don't put any more than 8 or 9 of these on an exam. 1, -1, 1. And then over here, B and C, 1, 2, and 4. Okay, great. Let's fill in the quadratic formula. Negative of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And I'll do the same thing here. A very common mistake in working with these things is not to draw that line underneath the b here out front. People just leave it out in space and then end up with the wrong answer. Negative of -1 plus or minus -1 squared minus 4 times 1 times 1 over 2 times 1. The double negatives become a 1 plus or minus the square root of 1 minus 4 over 2. Or 1 plus or minus the square root of -3. If you end up with the square root of a negative number, get rid of that negative out from underneath the radical. And the way we're going to do that is we'll write that as, yep, I'll write that as square root of -1 times square root of 3, or as Reagan just said, I times the square root of 3. Now, I'm okay with it here in terms of the root, but WebAssign might want it broken down a little bit farther like this. Square root of 3 over 2 times I. And the reason for that reflects the applications of this kind of stuff to physics, where the real part and the imaginary part have much different interpretations.
Does it matter if the i's in front or behind?
Here I wrote it next to it. You can write it up here, just as long as you don't write the I underneath the square root. It's not that we can't take the square root of I, we can, but you have to wait till trigonometry to get to the square root of I. Say again?
Is it still over 2 the I?
Well, it's being multiplied by square root of 3 over 2, so yeah, the 2 is in a sense dividing, this product. Let's take a look back and do the other part of this one as well. Maybe you've already done that during our chatter. So the negative of 2 plus or minus the square root of 2 squared minus 4 times 1 times 4 over 2 times 1. So that's going to be the square root of -12, I think, underneath here. Let's see. -2 plus or minus the square root of 4 minus 16 over 2. -2 plus or minus the square root of -12 over 2. -2 plus or minus. Now here I'm going to break this up into 3 roots. Out in front, I'm going to put the perfect square, which is going to be 4. Let's not forget to split off that -1. Now if I have a factor of 4 and -1, what's that leave me with here? 3. So overall, I end up with negative 2 plus or minus 2i square roots of 3 over 2. And I wish I could tell you we were done here, but we're not. Reagan sees it. Does anyone else see it? What's the common factor that I'm going to take out of the numerator? 2. Perfect. Nick, if I take out a 2 here, what's that leave behind?
Oh, well, it would be a negative 1.
Negative 1 plus or minus.
I. Square root of 3.
Perfect. And now I can get rid of the 2 in the denominator and end up with negative 1 plus or minus I times the square root of 3. Whew. Wow. Well, I think that's a total of 4 solutions. We've got 2 here, 2 here, we've got negative 1 and 2, so that's 4 solutions. Sweet. Let's see if we can't put all that together now and write P of x as the product of linear factors. So, let's see here. Don't know about you, but this is dragging onto my 3rd page here. So let's take a look at our roots. We have roots at x equal negative 1, x equal 2, x equals, let's see, negative 1 plus the square root of 3i, x equals negative 1 minus the square root of 3 times I, x equals 1/2 plus the square root of 3 over 2 times I, and x equals negative 1/2 minus the square root of 3 over 2 times I.
Why did you make it 1/2 and then -1/2?
Oops, I shouldn't have. Thank you. Actually, I think it was just a speck of dust on the lens, but I got it out, so thank you. Let's take a look at the corresponding binomials. Here, these are pretty easy. Just move everything over to the left-hand side. X plus 1 equals 0. X minus 2 equals 0. This one, a little bit messier. X plus 1 minus the square root of 3 times I equals 0. And x plus 1 plus the square root of 3 times I equals 0. You can write the I in front. Actually, I kind of prefer it out in front because you could accidentally get a little sloppy and draw that square root over the I. That's not going to happen in this course. Let's do the same thing here. This is going to be x minus 1/2 minus the square root of 3 over 2 times I. Finally, x minus 1/2 plus the square root of 3 over 2 times I. Oh boy. Wow. So, all of these are the binomials that we're going to multiply together. And this is the factored form of the P of x that we started out with. So, either write real small or grab a nice half of a yard of paper and let's finish this up. P of x is going to be x plus 1 times x minus 2. And all I'm going to do is just list all these all the way down. Times x plus 1 minus, I'll write it as I times the square root of 3. And x plus 1 plus I times the square root of 3. Times, I'm just going to come down here because I know I'm going to run out of room. Times x minus 1/2 minus the square root of 3 over 2 times I. And x minus 1/2 plus the square root of 3 over 2 times I. So an awful lot of busy work in this problem, but eventually we get down to the product of linear factors. Now, if you look at this, you've got an x times an x times x. All these leading coefficients are an x. So at least if I multiplied all these out together, I'd have x to the 6th power. If you remember way back about a half an hour ago, that's what we started out with, right? It's x to the 6th power. So it makes sense. Now, temptation of mine is to clear out the fractions and multiply it by 2. That would give me a 2x minus 1 minus the square root of 3 over square root of 3i. But unfortunately, that would put a factor of 2 here and here, and then the 2x times the 2x would be a 4x. It wouldn't match this anymore. So that temptation, got to fight it in this case. All right, awful lot on that one. If there's something that I went by too fast, you want to look back at it, let me know. Or maybe just be really happy to have this problem in your rearview mirror and never look at it again. Yeah.
I do have a question. Will
Yeah, please.
something like this on a test, like this length?
You know, I don't know. It depends on, you know, how my favorite football team is doing the weekend that I write the exam. So, yeah.
I don't think you ever mentioned, what's your favorite football team?
I need to know who to root for.
Yeah. I've been kind of circumspect on that. Anyone want to guess? I'll give you a hint. They're,
NCAA or pro?
no, NCAA.
Denver Broncos.
No.
Oh,
Yeah, I'll give you another hint. They're 5-0 and ranked 4th in the country.
U of M?
You're a
Oh, blue. Yeah. So, all right. So, I mean, all kidding aside, your grades are not dependent. Your exam is not dependent on the fortunes of a football team.
I don't know, with Wolverines, I wouldn't mind that.
Yeah. But I mean, it has happened that when they do well, you guys do well.
Yeah.
Just saying. So, root hard.
When's the state giving that up soon?
It's 3 weekends from this weekend. So, a couple more weekends out because we play.
Is it as a big house?
Maybe a
Is
month.
it-
It's in Ann Arbor. It's
Okay.
in Ann Arbor. Yep. So, okay, let's keep going. So, I mean, at least this matches a lot of what we saw. When we graphed the polynomial, we only saw 2 real roots. That meant that there was going to be 4 complex roots. Okay, perfect. The multiplicity of each of these was 1. We had a straight through and a straight through there. Again, it's matching what we expected. So, all right, let's go back to this and look at P of X. Do another one like this. It says factor the polynomial completely. And I know a couple of you might be gun shy, particularly after the very first problem, but let's take a look at this one. We've got 1 real root. Is that a bounce, wiggle, or straight through?
Oh no, zoom in.
Yeah, smart man. He's like, all right, zoom in. Yeah, what do you think now? Yeah, that's a wiggle, all right? That one's not just going straight through. That one lays pretty flat near x equals 0 for a while. So that one's a wiggle. So that means it has what kind of degree? Degree 3. And again, you can see that. That's kind of nice that we understand this bounce and wiggle stuff, because if you were to factor this out, that's going to be x cubed times x squared plus 2. And you can see you've got a root of multiplicity 3 at x equals 0. Okay, see if we can't find all the real roots and complex roots from that. I know that x equals 0 is a root, but I need to figure out where this has its roots too. So let's see, x squared plus 2 equals 0. That's x squared equals negative 2. What can x equal?
I.
A little bit more than I.
Plus or minus I times square root of 2.
Nice. So if you factor out the negative 1, that's plus or minus the square root of negative 1 times square root of 2. It's plus or minus I times the square root of 2. Yay. So we get x equals I times the square root of 2, and x equals negative I times the square root of 2. And once we know the roots, we can come up with the factors. So here we just got x equals 0, don't have to change that, but this is x minus I times the square root of 2. This is x plus I times the square root of 2. Those are your linear factors. So this one, this one, this one. I can put those all together into a polynomial form up here. So it's going to be an x, and then, let's see. But what power am I going to write for x?
3.
Yes. So it's going to be an x cubed. That's a horrible 3. Looks kind of like a 2. X cubed. And then you've got each of these linear factors. X minus I times the square root of 2. And x plus I times the square root of 2. There's your complete factorization. Beautiful. So there's our answer. All right. That one felt a lot better than, say, I don't know, example D. We good on that? Is he starting to get a little bit routine? Yeah? Okay. Thank you. Now there's something that maybe you've noticed about all these complex factors that we've run into. For instance, over here I had I times the square root of 2 and negative I times the square root of 2. Or back with example D, you had negative 1 plus square root of 3 times I and negative 1 minus square root of 3 times I, and so on, here and here. And even the first example, example A, we had positive I and negative I. So what kind of generalization might you start thinking of when you start thinking about complex roots?
There are always 2.
Yeah, there are always 2. They occur in these kind of pairs. If A plus BI is a root, then A minus BI is a root. Those are called conjugates. So this is the imaginary zeros theorem. Basically, it says if you have a polynomial with real coefficients, and that's an important part here, and you'll see them mention that all the time in talking about this, but you have to have something with real coefficients, then you're going to get roots at A plus BI and A minus BI. In other words, they'll occur in these conjugate pairs. Now that's actually very relevant for us as we look at example F. Let's see if we can't see what's going on with example F. I want a polynomial, I want to write a polynomial with these conditions. Q has degree 3 and zeros at x equal 3 and 2i. Now another thing about this polynomial is that it has to have integer coefficients. It means it has to have real coefficients. It can't have imaginary coefficients. When I put this handout for you together, I actually changed the problem from what the problem in the book was a little bit. Because the problem in the book gave you all 3 roots. I'm only giving you 2. I know that x equals 3i is a root, x equals 3 is a root, x equals 2i is a root. But I know I need another root if I'm going to come up with a degree 3 polynomial. What's that other root going to be? Julian?
Minus 2i.
Minus 2i. Awesome. Thank you. Now you've got your roots. Let's get the binomial factors. So it's going to be x minus 3 equals 0, x plus 2i equals 0. Excuse me, how about x minus 2i? Plus 2i is going to come below. Minus 2i and x plus 2i equals 0. So yay. If I want to find what my q of x is, q of x has to equal the product of these linear pairs. x minus 3, x minus 2i, and x plus 2i. Let me give you a hint as to how to multiply this together. Start with the conjugate pairs here. And the conjugate pairs are going to look like this. Those two. We're going to start by multiplying those two together first. So that means that that x minus 3 out in front, it's just going to get left here for the moment. That's okay. Now in between, you've got to FOIL this out. Although it actually turns out kind of nice. And I'm hemming and hawing to give you a chance to fill in these numbers for yourself. You've got enough here to do FOIL, right? Because there's two terms times two terms, so that's first, outside, inside, last. All right. Angel, maybe you can help me out. What do I get when I FOIL these together?
You get x squared plus 2ix minus 2ix minus 4i squared.
Perfect. So the thing that I was most looking forward is seeing that you got a 4i squared in at the end, but x squared plus 2xi minus 2xi minus 4i squared. Beautiful. We get some simplification here. Jason, what do you see that's going to simplify in the brackets here?
The 2xi would cancel.
Perfect. Minus 2xi and plus 2xi, those cancel. Excellent. Ella, what happens to the minus 4i squared term? Is there anything there?
Well, I squared equals -1, so it's -4 times -1, which is +4.
Well said. You got a career in education there. All right. So, yeah, it's I squared is -1, so -1 times -4 becomes a +4. And then x squared plus 4. Last but not least, let's multiply those together. So I'll do the x times the x. That's going to be an x cubed. And then the x squared times a minus 3 gives a minus 3x squared. X times 4 gives me a plus x, plus 4x I should say. And then finally minus 3 times times +4 gives me a minus 12. So there you go. There, actually, I guess I should, that should be a q of x. There's our polynomial. Whew. All right, 2 more. Looking okay on that one. I mean, it's nice, but keep in mind that when you multiply these things, you want to keep in mind that trick. There's going to be a similar trick, a little bit different, but some of that is going to play over to what we did over here. Now, in this case, we want to find q of x. Q of x with degree 2 and zeros at here, x equal 1 plus the I times the square root of 2. But they're only giving me one root. And Sean, I know I need 2 roots. So where's the other root?
1 minus I, square root of 2.
Perfect. 1 minus I times the square root of 2. So those are our roots. Let's look at the binomials. So if I move everything over to the other side, Noah, what would that look like?
1 plus I times square root of 2.
So moving it over to be -1.
I'm sorry. -1 minus I times square root of 2.
Perfect. And then x minus 1 plus.
Plus I times square root of 2.
Perfect. Thank you again. So I get to multiply these things together. So it's going to be x minus 1. I'll leave a little extra space around the x's here and around the 1. minus I times the square root of 2, and leave a little extra space here near the x minus 1 plus I times the square root of 2. So this. Now last I checked, FOIL had 4 letters. If you try and FOIL this, you're going to run out of letters. You need 9 of them, right? If you want to invent a word that helps you remember this, that's great. Now our brute force approach way would be to multiply the x times each of these 3 here, and then multiply the negative 1, and then multiply the negative I times the square root of 2, so that's 9 multiplications, and then you get to do all those additions and subtractions, add up like terms, simplify. Get the oxygen bottle. No thank you, all right? There's got to be a better way. Come on, Jeff, you've been doing this for a long time. There's a better way, right? All right, I got your back. Let's see here. Now, let's recall multiplying things together like this. A minus b times a plus b. Pretty simple, pretty straightforward. What do I get after all the hoopla and simplification? What are we left with? Go ahead, Jess.
A squared.
A squared minus b squared. Pretty simple, right? You just square the n terms and subtract them. This is the factorization of the difference of 2 squares. Or if you multiply them, then you get this. So how is that going to help me out over here? Well, I'm not sure you kind of caught it when we were going through it, but I did suggest to leave a little extra room around the x and the 1. The reason is I'm going to treat that as one whole term. So I'm no longer looking at this as, 3 terms here times 3 terms here. I'm counting it that as one term and that's another term. So basically this becomes the difference of squares factorization. It's like this here. Except what's my a over here?
X minus 1.
X minus 1. So I'll get x minus 1 squared. So x minus 1 squared minus something else squared. What's that other thing that gets squared? What's my b? Perfect, thank you. I times the square root of 2. Now, this first one here doesn't square out as x squared plus 1. There's a middle term here. When you square these out, you square the n terms, and then you take 2 times this times this. So you have a minus 2x in between. Not a bad idea to practice squaring these things out without repeating the binomial. Then what? Minus I squared is, Noah?
Negative 1.
Negative 1. And square root of 2 squared is? 2. So what we end up with is x squared minus 2x plus 1, and then a double negative is a plus 2. So overall, x squared minus 2x plus 3. So a little bit of finesse here at the end, but it's way simpler than trying to do this brute force. Brute force would be a real drag. So, comments or thoughts on this last little trick here? Okay. I don't think I'm going to take the time to completely do example H, but I'll talk you through the hard part. Hard part that you got to know here. You're asked to factor this, find all the zeros, etc. The thing to start with is what you know, right here. There's a root at 0, excuse me, root at 1, x equal 1. What multiplicity does it seem to have? as a multiplicity of 3. So what you're going to have to do is divide out the term x minus 1 from this polynomial a total of 3 times. So you divide it out the first time, and then it's still going to be a root, divide out the second time. And so eventually what you'll be able to do is write p of x as some x minus 1 cubed term times something else. And when you get it down this far, then you can use the quadratic formula if you need to. In fact, you're going to have to probably to find the remaining zeros, because the remaining zeros have to be complex, right? Because we got 3 real zeros. Overall, I know I have 5 zeros, so that means 2 of them have to be complex. So chances are you have to use a quadratic formula here. Sweet, sweet. All right, that's a wrap for section 3.5.